Okay, so on Friday, we talked about kind of stability of alkenes, and that was one thing. So this outcome is a little bit of a catch-all of a bunch of different things all related to alkenes and multi-alkene compounds. So quick recap on Friday, we talked about how with alkenes, you could tell if they were more stable or less reactive based on their number of substituents. If they had two substituents, they're more stable if they were trans, less stable if they were closer together. And then we looked at conjugation, which was a pattern where you had double bond, single bond, double bond, single bond, double bond, single bond. So if you had multiple alkenes, we could tell that they were more stable if they were conjugated than if they were by themselves. And then even more stable if they were in an aromatic ring. And we kind of left it on Friday as an aromatic ring being just benzene, but we got into a lot more details for that today. So the last little bit was not only kind of determining, we'll get to this at the end, aromatic, non-aromatic, and anti-aromatic, but also a little bit of naming. So this is your last naming for the semester. I hope that this naming is not overly complicated. The good news for naming benzene rings is that everything is flat, so there's no wedges and no dashes, so we never have R or S to worry about. We also don't really have to worry about E or Z because everything's going to be in a ring. I mean, you could have huge rings that are E, but for the most part, everything is just turning in a circle because it's in a ring. And then beyond that, it kind of adds one extra layer, but there's a lot of things we don't really have to count for when we are naming this way. So mainly the new thing with this is just memorizing kind of some names, many of which we've seen before in different aspects of substituted benzene rings, and then looking at kind of where other substituents are relative to them. So the main thing you do when you're naming benzene rings or substituted benzene rings, so you've got some names you need to know: pyridine, aniline. Benzoic acid is one we'd seen before. Benzaldehyde is one we'd seen before. Phenol, OL, is new to us, but hopefully that's phenyl with an alcohol. I hope that these are not overwhelmingly complicated namings. Most people tend to get these right. It's a lot less than the last ones that we've done that had E's and Z's and many, many different functional groups. All right, so the main trick to this is, not trick, but the main thing to this is keep in mind you still only have one main chain. And so while a benzene ring with a nitrogen is called what? Aniline, right. And then a benzene ring with an aldehyde is called benzaldehyde. It can't be both at the same time. So to figure out which one would be our main chain is the same way we've done in the past with functional groups. What's a higher priority functional group? Amine or aldehyde? Aldehyde. So this is your main chain right here, and everything else is just a substituent. So your main chain would be a benzaldehyde. This is the one that most people got wrong on this bridge. That's your main chain. Your main chain is the benzaldehyde. And then this thing is just a substituent. So that should seem familiar from past namings. You find the one main chain, everything else is just a substituent. So how do we name this little thing as a substituent? Amino, right? Amino with an O. So it's an amine kind of when it's a main chain, but it's amino when it's a substituent. And so the last new thing about this is that while you could number these, so this would be 1, 2, 3, more often than not, the way that it's done when you have a benzene ring or another aromatic ring is that you use ortho or meta or para. And all of those just tell you about the relative locations of them compared to each other. So ortho is right next door, para is directly across, and then meta's in between, so OMP. So this would be meta because they are not right next door and not directly across from each other. We only use that when there's exactly 2 substituents. When there's just one substituent, you don't need to worry about it. When there's 3 substituents, you need to use numbers. But when there's exactly 2, this is what we use. So this would be meta-amino benzaldehyde. All right. So moving over here, the main chain here, the highest priority is the alcohol. So this is your main chain. And this is what? Phenol, right? So PHENOL. Not to be confused with, and we saw this last naming, is that as a substituent, a benzene ring, anybody remember what this is called as a substituent? It's almost the same thing. Phenyl, yes. So phen-YL is benzene as a substituent. Phenol with OL is benzene as an alcohol. So those are very, very similar names, but like most alcohols, all is an alcohol. And like methyl is a methane substituent, ethyl, phenyl is just one as a substituent. So for instance, if you were to see this molecule right here, I know that's up in the corner. Your highest priority functional group would be this carboxylic acid. So this is your main chain. What's the name of that main chain there? Benzoic acid, perfect. So that would be a benzoic acid. There should be a space in between there. And then this is a substituent. So the other benzene ring would just be a substituent. So this would be paraphenyl benzoic acid. Phenyl being benzene as a substituent. All right, quick warning, we won't get into this too much in this class, but this thing right here, benzene with an extra CH2, this as a substituent is benzyl. And I only tell you that because benzyl is a thing, and benzyl as a substituent is different from phenyl. This is what you probably mean. Benzene ring as a substituent is called phenyl. Benzyl is actually a CH2 followed by a benzene ring. I have seen organic chemists who have been doing this for many years and have their PhD get this thing wrong. It happens. So I don't want to dwell too much on benzyl. It's a pretty uncommon substituent. But phenyl is the one I want you to really worry about. That's where benzene is directly attached. Just be aware if you say benzyl, and I mark it wrong, it's because benzyl is a thing. It's just a different thing. So this is phenol. So if this is phenol, this is your main chain. 3-carbon chunk is a propyl. So this would be, and they're across from each other. So this is para-propyl phenol. So don't forget to count your chunks. 1 carbon is methyl, 2 is ethyl, 3 is propyl. Propyl, people get it wrong a lot of times, but it's still propyl. And then butyl is 4. All right, these went really well, so I'm not gonna spend too much time on them. Aniline is benzene with an NH2. And then ortho is right next door, so orthomethyl would just be that. And then this is an example of a molecule where you have to use numbers because you have multiple substituents. So a benzoic acid is benzene with a carboxylic acid. And we don't number from this carbon, we number around the ring. So this would be your number 1. And you could go clockwise or counterclockwise, it doesn't matter. But what's a hydroxy as a substituent? OH, right. So dihydroxy at 2 and 4 would be an OH at 2 and 4. All right, any questions on any of those namings? All right, what other ones do we have from, do you remember what xylene is? It's a benzene with something attached. Yep, 2 of them. So this is a xylene. This is paraxylene right here with an X. All right, what about with just a CH3? Or to the T? Toluene, right. So these are molecules, you can probably go to Lowe's Hardwares and buy these. Toluene, benzene, they're all carcinogens, but they're all used as solvents. So these are things that exist. You probably find big bottles of toluene. But this is what toluene is, and this is xylene. They'll come up sometimes because they are aromatic hydrocarbons, and all aromatic hydrocarbons are some form of carcinogens. So we want to be careful with these, especially because they're volatile, so they're easy to breathe. So aromatic, the name comes from the fact that when people first found these, they do smell good. So that's where the name comes from. But for us, the name aromatic has a much deeper meaning now. So its roots are in smelling good, but really it's all about what makes rings more stable or extra unstable, or in the case of non-aromatic, just kind of normal rings. So you guys all wrote out definitions for this, and thanks for doing that. We're not going to spend a lot of time on that, but I do want to ask, how do we define this non-aromatic? Because to me, when I'm looking for these 3 things, that's the first thing I look for is non-aromatic. So what is non-aromatic? An interruption. All right, so let's be more specific. So non-aromatic, absolutely. It's a ring that has an interruption in what? Okay, and hybridization. So an interruption in the whole idea of aromatic and anti-aromatic is that they have p orbitals or pi bonds all the way around the ring. Not on substituents, that doesn't matter, but just throughout the ring. So it's a 5-membered ring, all 5. 8-membered ring, all 8. 6-membered ring, all 6. So those guys don't have an interruption. Non-aromatic are, I think, the easiest ones to spot because they have an interruption. So what would be an interruption? What kind of carbon or nitrogen cannot have a p orbital? Single bonds, how many? sp3. So how many single bonds would you have sp3? 4. So we have talked about hybridization before in that sometimes a lone pair likes to go in an sp3, but a lone pair could go in a hybrid orbital or a p orbital. So when we're talking about non-aromatic, we're looking for molecules that for sure have a defined interruption that is always a carbon with 4 single bonds or a nitrogen with 4 single bonds. So that interruption, you're right, it's an interruption, but it's interrupted with a carbon with 4 single bonds or a nitrogen with 4 single bonds, which is less common, of course, but usually it's a carbon with 4 single bonds. If you have 4 single bonds, you cannot have a p orbital. So therefore, you cannot be aromatic or anti-aromatic. And the difference between aromatic and anti-aromatic is all about counting the electrons. So the good news is that if you have an interruption, then you don't have to worry about the number of electrons. The ring is for sure non-aromatic. So just looking at these 4, let's go through these one at a time. Sydney, does this ring here, not the nitrogen, but the members of the ring, is there any spot that has 4 single bonds? Yes. So this carbon has 4 single bonds. You know that because neutral carbon makes 4 bonds and it's not making a double bond, so it must be making 4 single bonds. So this carbon right here is a for sure interruption in the p cloud all the way around. So therefore this ring is absolutely for sure non-aromatic. And then it doesn't matter how many electrons are in its pi cloud, because if it's non-aromatic, it's non-aromatic and you're done. So this is actually a pretty stable ring because there is conjugation, which is nice, but it's not at the level of an aromatic ring because it has that interruption. So we look at these pi bonds. A p orbital can arise in a couple different cases. Either when you've got a carbon that's making pi bond, it must have side-by-side p orbitals, right? And therefore this one right here can't. You can also have a p orbital if you've got a lone pair, because a lone pair can go into a p orbital, or it's possible to have an empty p orbital in the case of like a boron or a C+. But we'll get to all of those in more specifics. All right, so that is non-aromatic. All right, so we're just asking really right now, we're just looking at non-aromatic first. So looking at this ring right here, Olivia, is there any part of this ring that makes 4 single bonds? No. So this ring is not non-aromatic, and we're going to skip it for now. All right, Kylie, is there any part of this ring right here that makes 4 single bonds? Yeah, exactly, that carbon down at the bottom. So this carbon right here is making 4 single bonds. It absolutely cannot have a p orbital. So therefore, it is for sure interrupted, and it is for sure non-aromatic. Perfect. And we don't have to worry about counting the number of electrons in the pi cloud. So our work is done, and that's it. So don't sweat these too much in terms of the number of electrons. This one is really complicated because this pi bond here is kind of in the ring and kind of out. We'll talk about how to do that a little bit later. But the idea is that if it's non-aromatic, that's why to me this is the easiest one to find. Look for anything that's making 4 single bonds. And if any part of your ring, again, not outside of the ring, but inside of the ring is making 4 single bonds, it's non-aromatic and you're done. All right, Sydney, any part of this have 4 single bonds? No, good. All right, so these 2 are non-aromatic, and for these guys, we need to do a little bit more work. All right, so Olivia, how do we approach this one in terms of figuring out if it's aromatic or anti-aromatic?
Looking for counting the electrons, the pairs.
Pairs of,
Odd
yep.
is aromatic, and even is
Correct. Good. So I would recommend that you're probably going to say, I have to memorize that, because you kind of do. But go back to benzene. We know for sure that benzene is an aromatic ring, right? So if you forget, go back to something you know. Benzene ring is absolutely, the answer to this one is aromatic, because benzene is aromatic ring. We learned about that like week 2 of class. That was our one aromatic ring was benzene. You could call it either thing. And so now we have a lot more details, but the reason for that is you go through and you count specifically the electrons in p orbitals and pi bonds, because pi bonds are made out of p orbitals. And so anytime you see a pi bond, it's 2 electrons being shared between 2 p orbitals. There's 2 electrons being shared in that p orbital and 2 electrons being shared in this p orbital. All right, I know, so a double bond is 4 electrons, right? But we're not worried about the sigma bonds. We're only focusing on the p's and the pi's. So a pi bond here for a double bond, it's a sigma and a pi. The pi is 2 electrons. Here, the pi is 2 electrons. Here, the pi is 2 electrons. So that's your 3 pairs of electrons in your p/pi all the way around. Odd number of pairs, just as you said. Odd number of pairs in your p-pi cloud means the ring is aromatic. And what that means is that this ring is going to be extra stable and very hard to react because it's very stable. All right. Kylie, what about this one? Okay. Correct. So we know for sure that there are p orbitals here, 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 and here. Anytime you get a double bond, there's a p orbital. Right? That's how you make the double bond in the first place. So we know for sure that there's 2 electrons here and 2 electrons here. All right, we're going to go back a little bit to previous conversations that we've had. For an amine, all by itself, just sitting out there in the world, there's no aromaticity to worry about with just ammonia like this. It does have 4 regions of electron density. So all by itself, this would take the form of sp3, because that would be as far as it could spread its electrons out. But basically that nitrogen, it's not thinking, but it has a choice of where to put those lone pairs. And it would choose to spread them out because with no other contributing factors, that would be the most stable way to go. However, when you have this idea of aromaticity, which dramatically changes the stability of the molecule, it could always put its lone pair into a p orbital. So it would make things a little bit less stable for the nitrogen, but it would make it way more stable for the entire molecule. So the choice is always about stability. And so you might remember that this nitrogen all by itself, we would say is probably going to be sp3. And that would be true in a ring like this, where there are no, that's pretty sloppy, where there are no double bonds to worry about. With nothing else contributing to it, it would just put it in an sp3 orbital because that would be most stable. But that makes things a little bit more stable, as opposed to it can put its lone pair in a p orbital if that'll make the molecule way more stable. And the only time that that really pays out is with aromaticity. Aromaticity is kind of like, it's beyond resonance or anything that really we've discussed in terms of making things more stable. It's incredibly important. Like numerically, we saw that it made things 100 kilojoules per mole more stable, which was a whole lot. So if that nitrogen were to put its lone pairs into a p orbital, which is a choice that it has, then you would have p orbitals all the way around, and you would have 2 electrons in that p orbital, 2 electrons in this pi bond, 2 electrons in that pi bond. So between those 5 p orbitals, which go all the way around the ring, you would have an odd number of pairs. So absolutely right, aromatic is the answer to that. Perfect. How do we feel about those? Good? All right. So on this next page, I tried to put as many crazy examples as I could. I'm sure that some of them were very weird. I didn't want to go through and grade all of these because if you got all of these right, good for you. But it doesn't usually happen. But I wanted to try to come up with as many weird examples as possible. So we're going to go through all of these. I know that questions 6 and 7 are basically just circle the aromatic rings. That's a kind of question I'll ask you on a quiz. But for now, we're going to go through every single one of these one at a time and make sure that we understand all these different circumstances and why. All right, so anybody out there in Zoom who would like to take a chance, I'm gonna mostly just call on the folks in the classroom, but if you wanna try one, absolutely, you get more out of this by trying, especially if you try and get one wrong. So let me know if you wanna be called on or if you wanna try one. It's absolutely fine. I'm here, the volume's up, so go for it. All right, otherwise, we ready? Cindy, you ready?
Yeah.
All right, so let's start up here. So talk to me.
So we have two pairs so far of electrons. There's a pi bond at the end of each of those.
Okay, so we've got pi bonds here.
P orbital,
All right, hey, you're on the right track. Can I make a suggestion?
Yeah.
I would suggest that before you start to count electrons, you look for interruptions.
Okay.
So do that first. Just, I mean, like, again, there's a lot of different ways to approach this, and whatever works for you mentally is fine. But do you have anything in the ring that's making 4 single bonds?
No.
No, good. So it's not non-aromatic. The reason I suggest that is if you find that it's non-aromatic, then you don't have to worry about counting electrons because it doesn't matter. But in this case, you do because there's not an interruption. So keep going.
And then there is a C minus. So
Mhm.
that means that there's a lone pair.
Good. A C minus means a lone pair. This is really important. A C minus is a carbon with a lone pair.
And it's gonna want to make it an sp2.
Yep. Put that lone pair into a p orbital.
And it's aromatic because it
Perfect.
has 3 pairs.
Correct.
Oh,
So we've got a pair of electrons in this pi bond, pair of electrons in this pi bond, and a pair of electrons in this p orbital, which is an odd number of pairs. So this is aromatic. Good, good, good. Good? Everybody good with that? All right, Olivia, now I got a C plus.
So there's no interruptions, there's no carbons making 4 single bonds.
Good.
There is 2 lone pairs.
Who has a lone pair?
The sides of the double bonds.
Okay, they don't have lone pairs, but they do have electrons and pi
Right.
bonds. That's what you meant, right?
Yes.
Great, great.
Sorry.
You're good?
But it's a C plus, so it wants to, it needs more electrons.
So reactivity wise, that C plus is an electrophile. It would love more electrons.
Yes.
But we're not talking about reactions. We're talking about how it exists right now. So the question is, can or does it have a p orbital?
No.
C plus is the weirdest. This is probably the weirdest part of all of this is C pluses. So a C plus is a carbon with 3 single bonds and no lone pairs, correct?
Correct.
So how many regions of electron density does it have? How many places is it sharing electrons? 3, right. So it's basically sticking out its electrons in 3 directions. So that would be sp2. All right. So a carbon has 1 s orbital and 3 p orbitals. To make sp2, it hybridizes 1 s and 2 of its p's. So what does it have left over? Another p orbital. So that carbon has a p orbital. But how many electrons are in it? Does it have any lone pairs?
No.
No. So as weird as this is, a C plus has an empty p orbital.
So it's anti-aromatic.
Good, yes. So a C plus, and a boron is the same way, or aluminum. They make 3 bonds but have no lone pairs. They have effectively an empty p orbital. So a p orbital, yes, which was required to be aromatic or anti-aromatic, and you'd have p orbitals all the way around. But it doesn't have a lone pair, so there are no electrons in that p orbital. So these electrons can move through resonance all throughout this ring because there is a carbon that can make a double bond. And so this would absolutely have resonance, which we would like to say makes this ring more stable. But because there are, how many pairs? 2 pairs, it is anti-aromatic. So the result of this is that this ring is incredibly unstable. much like those cumulated dienes, the C double bond C double bond C, they are so unstable that we never see these in nature. If you look at drug molecules, biomolecules, you'll find rings all over the place. All of those rings that occur in biology and in life, they are all either aromatic or non-aromatic. You will never find anti-aromatic rings in nature. They're too unstable to exist. They would react with something. In fact, if you make this molecule, which you can make it in a lab, and put it in a jar, you don't even have to get that far, it'll start reacting with itself. As in, one molecule of this will react with its neighbor, and they will start turning into a big polymer because they can't stand to exist that way. It's too unstable. So anti-aromatic rings can exist momentarily, but the idea is they end up reacting with each other or with the atmosphere or anything because they're that unstable. So more often than not, anti-aromatic rings are things that we can draw, but they really will go out of their way to not even exist. So they're that reactive. So you won't find a lot of them. So in your problems, in your homework, you'll find a lot more aromatic rings and a lot more non-aromatic rings, and anti-aromatic rings are relatively rare.
What is something like you would find an anti-aromatic ring to be in or to make? Like, why would you want to make an anti-aromatic ring? Like, does that make sense?
Yeah, people make them for basic science reasons. That is to kind of, so applied science is like, I would want to make a ring that I want to, because maybe I want to try to cure cancer. And I think that this molecule that has these rings in it would be able to, cure cancer is a big thing, but, interact with this specific enzyme in some way. But anti-aromatic rings would not be something you could put into a pill or anything like that because they'll react with themselves. They'll react with the moisture, the atmosphere, or anything like that. So largely when people make anti-aromatic rings, it's kind of to prove a case. I'm sure there might be reasons that I'm not putting out there, but largely when you make these, it's a lot like, so the periodic table, all those big numbers at the bottom, kind of like that bottom row, seaborgium, etc. That's 106. Those are not elements that we find in nature. They're really radioactive and they don't exist for very long. And so people have made them in labs and they have to provide evidence that they have been made long enough to be able to identify them. But you can't keep a jar of them because they're so radioactive that they will react before you get any farther. So much anti-aromatic rings are kind of the same way. They're really unstable things that we can make for moments or minutes, but they tend to fall apart. And so it's more, we do it because we can, as opposed to any real practical reason. So aromatic rings are totally practical. Non-aromatic rings are totally practical. Anti-aromatic rings are just not. All right, Kylie, you ready? Perfect. Perfect. There's an interruption right here, so non-aromatic. All right, this is another weird one. It does have that pi bond coming out. We'll stop in just a second and I'll talk to you about how to do those. But let's finish this one off right here. All right, Sydney, go.
I don't think there's an interruption.
Correct.
There's 3 pairs of 2 electrons. And so I would say that it is aromatic.
Good. That's perfect and correct. All right, any questions on that one? I'm about to make this more complicated, but this is the correct answer. Everybody okay with that? All right, that nitrogen right there has a lone pair, correct? You didn't factor that in, did you?
No.
You should not have, which is good. So the deal is that nitrogen has a p orbital already. And you know that because it's part of a pi bond. You have to have a pi bond to make, or a p orbital to make a pi bond. So that nitrogen does not have the option of putting that lone pair into another p orbital that's right on top of the first one. You can't have 2 p orbitals on top of each other. If you've got 2 p orbitals, they'll be perpendicular to each other. So this lone pair is just sticking off to the side of the ring in the same way that this carbon has like a hydrogen sticking off to the side of the ring. They exist, but they're not doing anything. So I'm going to rewind a second here. In this example up here that we did on the previous page, that nitrogen could put its lone pair into a p orbital, which would be side by side with the other p orbitals. it could do that because it wasn't part of a double bond. If you're part of a double bond, it doesn't matter what else you do. You're already contributing a p orbital. You're already part of that pi system. So this nitrogen doesn't have a double bond, so it could put its lone pair in a p orbital. This nitrogen is part of a double bond, so it can't put its lone pair into a p orbital. This carbon right here has a lone pair, but it's not in a double bond, so it can put it in a p orbital. But for the sake of argument, if this carbon right here had a negative charge, well, it's already part of a pi bond, so it already has its p orbital that's parallel. So that lone pair is there, but it can't simultaneously be both in a p orbital and have a p orbital part of a double bond. Does that make sense? So the way you did that is perfectly correct. And it turns out, if you ever have a ring that is 6-membered with 3 double bonds, it'll always be aromatic. And it doesn't matter if you were to have an O plus over here, or an S plus right here, or a nitrogen right there, or a nitrogen with a hydrogen and a plus charge. It doesn't matter. If you ever see the pattern of a 6-membered ring with 3 double bonds, then for sure, everybody has a p orbital, and you for sure have those 3 electrons through your pi system, so it's always aromatic. So look for that. And if you see that 6-membered ring, it's aromatic, just the way you did it. Don't let the other things fool you. They don't matter. All right.
So will it try to get rid of those electrons, or is it just
No,
staying?
they're just there. Because the neutral nitrogen will have a lone pair, but those lone pairs don't contribute because it's already aromatic. So they're just there. It could use them to make a bond if it wants to, but they're not part of aromaticity. In the same way that like this has a hydrogen coming off, it doesn't contribute to aromaticity. There could be other things going on. It could be a benzene with lots of things coming off of it, but that benzene is still an aromatic ring. All right, so let's talk about this weird situation here, where you've got a pi bond that's part of the ring, but also not part of the ring. So we're gonna switch over a minute and we're gonna go to we're gonna do a little whiteboard. All right. So a ring like this is really hard to quantify because we do have p orbitals all the way around. Everybody see that? So here's a double bond that has a p orbital. Here's a double bond that has these p orbitals. But then a C double bond O does have 2 p orbitals, right? One here and one there. So there is conjugation through this ring, but when we ask about whether or not this ring is aromatic, it's really hard to answer because there's 2 electrons here and 2 electrons here. That's pretty easy. But what about these 2? They're not both in the ring, so they're kind of part in, part out. So the way that we address rings like this largely is, first off, it's kind of experimental. So there's no great answer to this just by looking at it on paper. You kind of have to take it in lab and play around with it. And what we find the answer to this is that this ring is really hard to make and super unstable, which should probably indicate to you that it's not aromatic. And the way that we justify that is through resonance structures. So what we try to do is make a resonance structure that fits our rules. All right, so the resonance structure that's going to really matter here has to do with this carbonyl, because having a pi bond between the ring and not the ring makes things really complicated. So let's think about the resonance structure of a carbonyl. We spent a lot of time over the last month talking about carbonyls. In carbonyls, which way are the electrons being pulled? More towards the oxygen or more towards the carbon? Who's more electronegative? The oxygen, yes. So in the only reasonable resonance structure of this, the electrons would be pulled towards the oxygen. And so it would look like this. And now we don't have that pi bond in between. So now we can just focus on this ring here and attribute aromaticity. And this should look like one that we just did a few minutes ago. If we go through and count out these electrons, we've got a pi bond here, so that's 2 electrons. We got a pi bond here, So that's 2 electrons. All right, Olivia, I called on you for this one. You remember it? So a C plus has a p orbital, right? Yeah, so it's got 3 regions of electron density. So it has a p orbital, and that p orbital has how many electrons in it? None. It doesn't have any extra electrons, so it's empty. So there's 0 electrons in that p orbital. So we don't have an interruption. We do have p orbitals everywhere. We have 2 total pairs. So this ring would be what? Anti-aromatic. Perfect. And so we use that justification to explain why, while this molecule here looks pretty simple and straightforward, it's extremely reactive and extremely hard to make. It's tremendously unstable, right? Because the resonance structure of it shows that it's or at least partially anti-aromatic. Right? On the flip side, if you guys ever look at the structures of like the bases in DNA or RNA, caffeine, a lot of those biomolecules, you'll see rings that have this kind of thing going on a lot. That's a nitrogen. Like kind of a ringed amide, which is a nitrogen in your ring next to a carbonyl. So this molecule right here kind of suffers from the same thing, where we can see there's a pi bond there and a pi bond there, and that nitrogen could put its lone pairs in a p orbital. But dealing with this carbonyl is a little bit more complicated because the pi bond electrons are kind of half in, half out of the ring. So once again, we justify this one through resonance. Amides have a really consistent resonance structure that would involve having an N plus and an O minus. There's our nitrogen. And looking at this ring now, that ring is absolutely for sure what? Aromatic. Yeah, it's that 6 members with double bonds all the way through. So I am not going to ask you things like this that you have to draw resonance structures of them to figure out on the quiz. But I do want you to see them because it is a question. What do you do? And usually in things like this where we can't really figure it out any other way, we approach it through resonance, because resonance structures exist and they're kind of 2 different ways to tell the same story or look at the same molecule. And it turns out that rings like this are aromatic and they're super stable. And it's not really by looking at them, it's kind of by considering their resonance structures. And then there'll be some weird rings like this that for some reason are really unstable, but again, their resonance structure is justified. Yeah. Yeah.
So I just want to make sure I'm not understanding, right? So like, basically like if you see like a carbon with like a double one option, something that's like happening without like that would have to do with the presence to figure out.
You would, but I'm not going to make you do that. Yes, but that's how you would have to approach that. Yeah, and I can come up with even weirder examples that like the only way I would know is to like make an educated guess. And I'm not really into things that you guys are having to make guesses on because I don't think, like a lot of those things, what we end up having to do is look it up or go into the lab and try to figure it out using data. And so those aren't things that I could ask you to do in a quiz. And so I'm not going to. Does that make sense? Okay. But I want you to see this kind of ring because this ring shows up a whole lot, especially in nature and biology. You'll see this kind of thing a lot. And I doubt that you would say to yourself, Dr. Moore, is this an aromatic ring or not an aromatic ring? It probably wouldn't pop into your mind, but I would prefer that you have seen those and seen that we do have answers, but it kind of takes a little bit of a backwards approach. All right, so let's go back to ours. So I did ask you some that had that carbonyl, like this one right here, but this was non-aromatic, so it didn't really matter how those electrons contributed to anything. All right, moving on down. My hope is that these kind of get faster and faster the more you practice them. So Sydney, are you up? I think you're up. This one right here.
So there is an interruption.
Perfect. Perfect, yes. Good, good. All right, Olivia.
So it's a 6-membered ring that has 3 double bonds, so it's always going to be aromatic.
Perfect. And the fact that there's a plus charge doesn't matter. The times that a plus charge matters is when you're trying to figure out whether or not that carbon has lone pairs or not, to figure out whether or not it can have a p orbital, to figure out how it can contribute to aromaticity. But we know for sure that this nitrogen has a p orbital already because it's part of a pi bond. So none of that ancillary information factors into this at all. So yes, this is aromatic. Everybody good with that? All right, Kylie. Okay, good. Okay, so let's figure this out. So that oxygen, you're on it. That oxygen does have 2 lone pairs. Could it put 2 lone pairs into one p orbital? No. Could it put a lone pair into one p orbital? Yes. So the best that it can do when it comes to all of this jazz is to put one of its lone pairs into a p orbital. Theoretically, it could put two lone pairs into 2 p orbitals, but only one of them would be parallel to the rest. Yep. Perfect. Yes. And this is furan, which is a ring. You might remember THF from our BH3.THF reaction. That was tetrahydrofuran. It looks almost exactly like this ring. But this is a pretty common ring. We can buy bottles of this. It's an aromatic ring. It's really stable. All right. We're sawing through the wall over here. Sydney, here's a fun looking little ring. What do you think?
I think it has 2 interruptions.
Yeah, it does.
So it's non-aromatic.
Correct. So once again, we don't need to worry about counting the number of electrons in pi clouds because it doesn't matter. There's just a double bond over here and there's a carbonyl over there, and that's all we have to worry about. All right. So if you can see a question like this, which one's aromatic, you can just look for the aromatic rings, but for today, we're going to go through these individually. This one we saw already. Libby, you got to do this one already. You remember what it is?
It is anti-aromatic.
It is. All right, we'll skip that one since we did that one already. Sorry for putting the same problem in here twice. All right, so let's move on. Let's do this one. Aromatic, how do you figure? All right, I'm going to try to be a turd. Don't fall for it. But this has a lone pair.
It's not going to share any orbital.
Correct. It does have a lone pair, but it can't put it in a p orbital that's side by side because it's already in a double bond. So it's already making its p orbital. So that lone pair is just sticking off to the side doing nothing. Well, it exists. But, and you could say this is a nucleophile. Sure, this is true. In fact, this ring would be basically impossible to make, but it is aromatic. All right, we're moving into some weird ones. Kyle, you ready? Okay.
Okay, I think, would it be non-aromatic because there's only one pair of electrons?
All right. Do we have an interruption? No. So it's not non-aromatic. So let's work through to the pairs. So we have a p orbital here, right? And here. And how many electrons are in that pi bond? You got the right answer here. You got the right, you're on the right path. So what about that C plus? Correct? All right, she just said it has a p orbital, but there's 0 electrons in it, all of which is perfectly correct. So you have p orbitals all the way around the ring. Yes. And how many total pairs do we have? 1, yes. Is 1 an even or an odd number? Yes. So this would be, yes. So this is an aromatic ring. Yep. This is the weirdest aromatic ring that I think I could possibly draw. But we've got p orbitals everywhere, and our total number of pairs is 1. So 1 pair, 3 pairs, 5 pairs, 7 pairs, 9 pairs, 11 pairs, whatever is an aromatic ring. Okay. Now we've seen that one, and so it won't be a surprise, but it is super weird when it first pops up like that. All right, Sydney.
So it has 2 pairs so far,
electrons. And then the NH has a lone pair on it that can make it have a pi and also another pair, which makes it 3, and it is aromatic.
Yes. All right, I'm going to ask you guys an acid base question about this one in a few minutes. But yes, this is an aromatic ring. I hope you guys have kind of seen this trend, but aromatic rings usually, besides these weird ones, mostly come in 2 flavors. Either they are 6-membered rings with double bonds everywhere, or 5-membered rings in which there's 2 double bonds and something with a lone pair. So we're going to flash back. See this 5-membered ring? It's got 2 double bonds and something with a lone pair. 5-membered ring, 2 double bonds, something with a lone pair. So this is a 5-membered ring, 2 double bonds, no lone pair, so it's not aromatic. But here's one that's 5-membered ring, 2 double bonds, lone pair, aromatic. I mean, still walk through the process of this, but I want you to kind of be able to spot these because it's really mostly just the same 2 things. Here's another aromatic ring. This is the same one, it's just upside down. 2 bonds, 2 double bonds, and something with a lone pair. And that's what we tend to see over and over again, is aromatic rings come in one of those 2 flavors, for the most part. You still need to be able to walk through the process because I could give you a 7-member ring or something crazy. But that's how we mostly see these things in nature. All right, we're almost done. Who's up? I forget. You're up? You're up? I don't know. Who did this one? Okay. All right, so what's this one?
Aromatic.
Great. All right, don't fall for this. But look, this carbon has 4 single bonds. It's not in the ring, so it doesn't matter. All we're worried about is the carbons in the ring or the atoms in the ring. Okay, good. All right, what about this one? Non-aromatic, perfect, because you've got an interruption there. Lovely. All right, Sydney, here's my final weird little tiny ring.
I'm gonna say it's aromatic. It has that 1 pair of electrons right there from the pi bond.
Okay.
And then I don't think that's an interruption.
It's not an interruption, you're right, because it does have lone pairs.
So I guess one of those makes it.
Uh-huh.
So actually it's anti.
Perfect, yes. You talked yourself into the correct answer. This ring would be anti-aromatic. It is going to be impossible to make for that reason. So this would only be something you could draw, not something you could really have in lab. But this would be an anti-aromatic ring. Once again, if you've got 2 lone pairs, you can only put one of them in a p orbital that's side by side with everything else. So we can't say that we count this lone pair and that lone pair. Each of your members of the ring can only contribute 1 p orbital to your pi plot. All right, this is the last one.
Anti-aromatic.
How so?
Because there's 2 p orbitals, so they're making 2
Uh-huh.
pairs of lone pairs, but the oxygen doesn't offer any, it doesn't have any electrons. No.
So a C plus is a carbon with 3 bonds and no lone pairs.
Yes.
An O plus is not the same thing.
Not the same thing. So it does have a lone pair.
It does have a lone pair, yes. You will never find an oxygen without a full octet or a nitrogen without a full octet. So it does have a lone pair, yes.
So it's aromatic.
Perfect, yes. So quick refresher. There's nitrogen neutral. There's nitrogen plus. It always has a full octet. This is oxygen minus. 3 lone pairs, 1 bond, full octet. Oxygen neutral, of course, looks like this. And then O plus would have a 3rd bond, but still a lone pair, still a full octet. So that's really the only time that these charges matter, is you need to know how many lone pairs they have. And C plus will be the only thing that doesn't have a lone pair as that empty p orbital in terms of plus charges. All right, how do you guys feel about these? I know we went through some weird examples, but you see the patterns, repetition. This is the kind of thing that if you practice it enough, it just gets repetitive. And I will run out of examples to ask you because eventually there's only so many like 5 and 6 member rings. All right, we got 10 more minutes. I'm gonna give you a couple questions that are gonna be a little integrative of stuff we've done already, but hopefully we feel pretty good about this. What is gonna be on your quiz is probably what you could expect, what we did on Friday. I'll ask you which of these double bonds is more reactive, or which of these rings is more stable, or all of that good stuff. You need to factor in everything, those 4 trends we went through on Friday. And then for today, there's going to be some naming of some type, probably not a lot. And then some, is this ring aromatic, anti-aromatic, or what? All right, so here is a ring. It is a nitrogen. It is pretty basic because most neutral nitrogens are pretty basic. What do bases do? They share electrons with what do bases react with? Acids, right? So it's going to share electrons with an H plus. You say they take on H pluses? Yes, they take on H pluses. They share electrons with hydrogens. All right, good. So this reaction is totally reasonable. This happens. This has a pretty reasonable pKb. It's a pretty reversible reaction. Give you a plus charge. No big deal. It's just like any other amine. This molecule, on the other hand, is an incredibly poor base and absolutely does not work very well. So this one is a fine weak base. And this one is barely basic at all. Ooh, I changed colors. All right, so why? First off, what does this thing become when it acts like a base? What would be different in the product? Two H's. Yep. So why is it that this reaction has really no problem going forward, and this reaction absolutely loathes going forward and loves going backwards?
Because it's already so weak.
Don't think about this in terms of acid base. Think about this in terms of what we're doing today. Yes. So let's look at this one. When this ring acts like a base, it turns into this ring. So let's classify these rings as we've been doing today. Is this a ring aromatic, anti-aromatic, non-aromatic? Non, right. Because it's got all kinds of interruptions. In fact, it doesn't really have any pi bonds. All right, what about this ring that it becomes? Non. So that doesn't really matter because it's not changing anything really about the stability of the ring. So talk to me about this reaction.
I'm assuming aromatic.
Don't assume, tell me for sure. We actually did this one.
Aromatic.
Okay.
I know it's aromatic.
You know that this is aromatic, yes.
The bonds make
Yep.
a pair up there.
Yep.
The lone pair.
Yep,
And
yep.
the bonds, so there's 3 pairs.
Yes, so
And
this
the
is an aromatic.
aromatic is more very stable.
Correct, but what does it become if it shares that lone pair to make a new bond?
Becomes non.
Yes, so this nitrogen has 4 single bonds. So this is an example of an interruption with a nitrogen. It's anything that has 4 single bonds cannot have a p orbital. So therefore, in order for this reaction to occur, not only would the N become an N plus, which is not that big of a deal, but it would stop being aromatic and start being non-aromatic. So it would have to go way up in energy because it's losing that super stability of an aromatic ring. So this is something that would be completely unanswerable before today. But what we see is that sometimes rings behave weirdly or react weirdly. And a lot of it is predicated on the fact that if you start with an aromatic ring, it really doesn't want to react, particularly if it's going to lose its aromaticity. Because aromaticity, or being aromatic, is really, really, really a stabilizing force. For a molecule like pyridine, it wouldn't really matter that much. Because notice that, so this is pyridine, and it does have a lone pair, but the lone pair is not part of what makes it aromatic. So if this guy acts like a base, it would become this ring, which is called pyridinium. But Olivia, this ring is what here? And this ring is also aromatic. These are both aromatic. So in this case, there are reasons why this is a little weaker base than most amines, but it's still aromatic. So it's not that big of a deal for it to act like a base. So if you're not changing the classification of your ring, then the ring itself actually doesn't matter very much. But if you're going from aromatic to non-aromatic, they do not like to do that. On the flip side, this thing would be very, very acidic because by giving away a hydrogen, it would become aromatic. All right, questions on any of that? Sound good? Okay, so again, this is a little beyond what I'm going to ask you about, but your final will be integrative of multiple things. So I want you to kind of see this kind of stuff. All right, my last thing is I want to show you some kind of weird bigger rings, especially multicyclic rings. So molecules like this exist. And there's multiple ways of thinking about these. But largely, probably what you can see from this is that there's two different rings. And you could kind of say that this one is aromatic. And you could also say that this one is aromatic. But it kind of depends how you count those electrons. They can't really be in both at the same time. And so the way that this ring ends up working out is that it is aromatic, but it's only kind of about the stability of one aromatic ring, not two. So if you want to think about it kind of like the electron spinning around in a circle like resonance, you can only really do it one side at a time. And so rings like this, usually what happens is they are aromatic, but they're not like as stable as two aromatic rings would be. And so another way of drawing this, if we actually move its electrons around, you can kind of see that if I take that left ring and I do this with it, that you can kind of see that there's a smear here of, kind of imagine that this bond is in here. It's actually 5 pairs in one really big ring that has like a bridge in between. And so it's kind of like one big aromatic ring as opposed to 2 aromatic rings at the same time. So some of these are a little bit weird to think about. And we do have all kinds of weird rings that exist. All right, and for the most case, what these things end up doing is they end up mostly acting kind of like one big aromatic ring. So ignore kind of those bridges in between. You can kind of see that this is like one huge ring that has 1, 2, 3, 4, 5, 6, 7 pairs. So it kind of acts like one big aromatic ring instead of 3 little aromatic rings. So that's kind of what we do when we have these big rings. Again, this is a little beyond the scope of what I'm going to quiz you on, but I wanted you to see these things because they do exist. They are kind of weird, but usually what happens is they end up kind of acting just like one big aromatic ring instead of lots of extra stability for lots of aromatic rings. All right, questions on any of that? Does that kind of make sense? So they just end up usually being like one aromatic ring. You could, of course, draw some that are anti-aromatic, but mostly they just don't exist. We can't make them. All right, any questions on any of that? Know what you need to do for Wednesday's quiz. Okay, quick refresher. We have lab today and tomorrow if you're in group B. If you're in group A, you do not have lab today and tomorrow, and you do not have lab next Monday and Tuesday. So this is our last class for a while. because you're having you have your Easter break on Friday, and we kind of extended that into a spring break of organic chemistry going into next week. So we don't have class this Friday. We don't have class next Monday. We don't have lab next Monday or Tuesday. And we do not have a new quiz next Wednesday. So we're kind of taking a week off of this Wednesday through Wednesday plan. You do, however, there will be makeup quizzes next Wednesday if you need them for retakes, because I don't want those to get too far from your memory. So we will have retakes if you need them next Wednesday. But besides that, this Wednesday is normal quizzes. Today and tomorrow are normal for lab, but then we kind of have a week off after that. I know we've had a lot of time off for lab because of my health, and I'm sorry about that, but good news, we haven't really missed a lot of class. So this will be kind of a break from class. I know, and I'm sure you all could use a break as well, because we're making it through this semester one way or another. All right, thanks. I'll see you all in lab or sometime.
You have 2 seconds, Dr. Ring?
I do have 2 seconds.
I missed this part when on the second page of the bridge, it was the second one down, or the second row of the first one, the ring that had the NH and the OH in it. Why is that one non-aromatic?
Hold on, let me pull it up.
Yes, sir.
So this one, right? All right, so tell me where.
It's on the question 5, classify H1, right there.
This one?
Yes, sir.
Okay, so you've got that carbon right there in the lower right-hand corner. It has 4 single bonds. And anytime you have a carbon or a nitrogen with 4 single bonds, that means that that carbon cannot have a p orbital, and therefore you do not have p orbitals all the way around, and therefore you have a non-aromatic ring.
Okay, I'm sorry I lied. It was the one below that.
Okay. This one right here?
Yes, sir.
Okay. So the trick to this one is that whenever you have something with 2 lone pairs, you can only ever put one of them into a p orbital. You could put both in 2 p orbitals, but they would have to be perpendicular to each other. So when we're thinking of the p orbitals that contribute to this extended pi cloud or p cloud, they all have to be parallel to each other. So as we looked at this, the way that it's drawn, they would be kind of coming out at you. So they'd all have to be parallel to each other. And so this oxygen can put one lone pair into a parallel p orbital. The other one would be perpendicular, so it wouldn't matter. And so it ends up being aromatic because only one of those lone pairs can go in a parallel p orbital. There's 2 electrons from that pi bond, 2 from that pi bond. That's 3 pairs, so aromatic. This other lone pair would just be sticking off to the side in the same way that this lone pair would just be sticking off to the side. You can only ever have one lone pair, and this really usually matters for oxygen, which has 2. You can only have one lone pair that is in a parallel p orbital.
So just to clarify, say some way that you had like one lone pair instead of the 2, would that still count as aromatic?
Yes. So for example, this one down here, this is a very similar type of problem, but instead of having 2 lone pairs, this nitrogen has 1 lone pair and a hydrogen. And the hydrogen doesn't matter in the same way that the second lone pair here doesn't matter. If you've got a lone pair and you're not making a double bond already, you can put a lone pair and only one into a p orbital, and that one can be part of your p pi cloud. So that can count towards aromaticity.
All right, thank you very much.
You are welcome. I will see you later.